signal flow graph representation. Okay, I welcome everyone to this video lecture on signal flow graph representation. Okay, chapter number 6, module number 2. Okay, so as we have seen in our previous class regarding the block diagram reduction and block diagram reduction techniques. Okay, so this is the continuation part of the block diagram. Okay, so here what we are going to do is, instead of drawing the block diagram, here we will go with signal representation. Okay, it is much simple than compared to the block diagram. Okay, here we don't have any block diagram reduction rules. What we have seen in the block diagram, like blocks are in parallel, we need to go for multiplication. Blocks are in addition. Blocks are in series, we go for multiplication, right? We need to reduce the minor loop, right? Major loop, shifting of takeoff points, shifting of summing points after the block, before the block. Okay, there are almost some n number of 7 to 8 number of rules were there in block diagram. Here we don't have any rule for the signal flow graph. Here we have some techniques, some properties of signal flow graph. Okay, so before going to signal flow graph representation and studying the signal flow graph, let us find, or let us try to define what is signal flow graph. Okay, so once we go for signal flow graph, the outcome of this signal flow graph session will be, you will be able to represent the given physical system into a signal flow graph. This is the outcome of the today's session. Okay, because we are transforming our complete application into a block diagram. Okay, so and then after block diagram we'll try to go for finding the signal flow graph, and then at the last again we will end up our discussion with finding the transfer function for the given block diagram, or finding the signal flow graph. Okay, so this is the outcome of today's lecture. So let us start with the new topic here. Okay, that is signal flow graph. Okay, what actually this signal flow graph is? Nothing but this signal flow graph. Here we'll study some introduction part, some definitions, small definitions are there with respect to signal flow graph. Okay, and some terminologies related to signal flow graphs and few examples. Okay, so introduction part says the graphical representation of the variables, okay, of a set of linear algebraic equations representing the system is called signal flow graph. Okay, so whatever the block diagram we have in the earlier module, okay, so those modules will be represented by a set of some algebraic equations. Okay, and those algebraic equations, okay, are nothing but your equations for the given signal flow graph. Okay, then what you are going to study here in signal flow graph, and what this signal flow graph will give you is nothing but it will give you again the transfer function, the flow of the input variables towards the output side. Okay, here we will be having some kind of other parameters. Okay, then we will see one by one how this signal flow graphs will give us more information related to any application, okay, or related to any system block diagram. Okay, in short, this signal flow graph is represented by SFG. Okay, you remember that is SFG means signal flow graph. Okay, then what this signal flow graph will show is, this signal flow graph shows the flow of signals, right? Flow of signals means how the signal is flowing from one point of the system to the another point of the system. Okay, and this signal flow graph also gives us the relationship among the different signals. Okay, if I have more than one signal, it gives us the relationship between the signals, or among the signals, or with respect to one signal to another. Okay, but if you want to go for the transformation from the block diagram to the signal flow graph, okay, you need to study the signal flow graph, its parameter, okay, its different sections of signal flow graph. Basically, the signal flow graph consists of, okay, branches, okay, which represents signals and nodes. As we have seen in the block diagram basic elements were the transfer function block denoted by G, right? We have summing points and takeoff points. Similarly, here in signal flow graph, it consists of branches. Just like a tree has branches, similarly, the signal flow graphs also have few branches, or it can be one branch, or it can be many branch. Okay, and that represents the signal and also nodes. Now, let us consider one simple example, okay, of equation V is equal to I into R. The Ohm's law says that the voltage flowing through the conductor, or the voltage flowing, is directly proportional to the current into the and the resistance. V is equal to I into R. Here V represents voltage, I represents the current, and R represents the resistance of the circuit. Okay. Now, if I want to construct a signal flow graph, okay, if I want to construct a signal flow graph for this particular equation, V is equal to I into R, okay, I need to go for this diagram. Okay, here V represents my output, okay, I represents my input, and R is nothing but my internal resistance of particular conductor. Okay, so the signal flow graph for the given equation is, you have two nodes, you can see here. Okay, you can see the dotted lines representing here, this is one node, okay, and I have one more node at the output side. Okay, so I is nothing but your input, V is nothing but your output, and these two are nothing but your node. Okay, that is what the definition of signal flow graph says. It basically consists of the branches, okay, which represents the signals and nodes. Okay, so here my signal is current I and voltage V, okay, and they are represented by nodes, one node for I, another node for V, and they both are connected through a line segment, okay, represented by a small arrow, and this is nothing but R, and your R is nothing but your resistance, okay, which shows in this particular direction. And the line joining between these two nodes, that is I and V, is nothing but branch. Okay, so this gives us the complete definition or of signal flow graph. Okay, now what this signal flow graph consists of? Again, it also consists of some kind of dependent variables and some independent variables. Both dependent and independent variables are represented by nodes. If you look at this diagram, okay, I have two nodes, one is current I and another voltage V denoted by V, and these are nothing but two nodes. So basically, if you say the equation V is equal to I into R consists of two nodes, okay, and one internal resistance represented by R. Okay, so this signal flow graph consists of both independent and dependent variables. They are represented by basically node, and the relationship between the various nodes are represented by joining the nodes as per the equation. If you look at this diagram again, okay, I have just joined these two nodes from I to V, okay, and this gives me the relationship between the two nodes I and V. Definition. Okay. Therefore, this is how the signal flow graph is represented. I will just show you again. Here you can see in this signal we have some properties. Okay, so the properties of signal flow graphs are: the signal flow graph is applicable only to linear time invariant system. Okay, that is the first property. You cannot apply to non-linear signals or simply linear time variant system. So here we can apply only for linear time invariant systems. Okay, then the second property states that the signal in the system flows along the branches, okay, and along the arrowheads associated with the branch. Okay, the property says always your signal when you apply, okay, it flows along the branches. Here you can see in figure 6.3 you have one node x1, one node x2, okay, and your signal is flowing from x1 to x2. How it is? Just see the arrow mark. The direction of this arrow mark is towards x2, okay, that is along the arrowheads. So it means that you should be very careful to analyze the signal flow graph based on the representation of arrow mark. Okay, so sometimes the arrow mark can be towards x1 direction. Okay, so that is called as, that is nothing but your backward loop. Okay, we'll see one by one. Then the third property of signal flow graph states that the signal gets multiplied by the branch gain, okay, or it is also known as branch transmittance, okay, when it travels along it. Okay, this point multiplication is nothing but, just look at this diagram here, 6.3 figure. X1 and X2 are the two nodes, and the number 4, okay, the number 4 represents branch gain. Okay, first you need to know what do you mean by branch. Branch is nothing but the line joining between the 2 points is called as branch. Okay, and this branch has some number represented by 4, and this 4 is nothing but gain. So always remember the number which is written or the value which is written in between the two nodes it represents branch gain, or it is also known as branch transmittance. Okay, and how it is calculated? It is calculated simply by multiplication. Okay, simply by multiplication. If I want to find the value of x2, then the value of x2 is equal to 4 multiplied by x1. Okay, just in as we have seen in block diagram, a general block diagram is multiplied by its input. Okay, so similarly here also we do the same thing. Okay, then property number 4, the fourth property of signal flow graph is the value of variable represented by any node is the algebraic sum of all the signals entering the node. Okay, it means that if you want to calculate any node equation, okay, then that particular node gives you the algebraic sum of all the signals entering at the node. It means if you have more than one signals, okay, entering one particular node, if you look at figure 6.4, okay, two signals x1 and x3 are entering the node x2. Okay, and if you want to find the equation for x2, then this x2 is represented by the algebraic sum of these two nodes entering. Okay, just look at this equation. How to write the equation? X2, okay, x2 is equal to 4x1. You can just look at this equation. Okay, so x2 is equal to 4 multiplied by x1. Okay, this is the property says branch gain should be multiplied with the input. Okay, so 4 is multiplied with x1. Okay, so 4x1 minus, okay, why it is minus? Because the gain between this x3 and x2 is minus 2. If it was plus 2, then we would have written plus 2x3. Okay, so therefore here if you want to calculate this x2, okay, so x2 is equal to 4 multiplied by x1, that is gain multiplied by the input node, okay, minus 2 multiplied by x3, right, minus 2 multiplied by x3. We have one more node represented by x4, which is moving towards the point x2, okay, which has gain x3. So therefore plus we can add here, that is 3 multiplied by x4. So always remember, if you want to find any node equation, then this equation can be obtained by the algebraic sum of all the signals entering to that particular node. Okay, so this is the fourth property of signal flow graph. Then the fifth property of signal flow graph is, if you have some n number of variables, okay, represented by some nodes. Okay, look at figure 6.5. We have node x1, okay, we have x3, we have x2, x6, x5 and x4. So the number of branch leaving a node does not affect the value of the variable represented by that node. Okay, so if you look at this figure number 6.5, in 6.5 at x2, so the entering points are x1, okay, entering points are x1, then x3, okay, x4, x5 and x6. Okay, so if you want to find the node equation of that particular point, okay, then the property says the number of branches leaving a node, okay, does not affect the value of variable represented by that node. Okay, then let us take an example, that is x2. Okay, what is x2? x2 is equal to 5 multiplied by x1 minus 2x3 minus 2x3. Okay, then what about the other? You can see there is a difference between this x1, x3, x4, x5 and x6. Okay, how it is? Just look at here. Okay, the node x1 and x3 are entering points. Look at the arrow mark. Okay, look at this arrow mark. Arrow mark at 5, arrow mark at 2, they are entering towards the point x2. So that is why the reason in the given equation you have 5x1 minus 2x3. Okay, I cannot write these equations for x4, x5 and x6. Why? Because the arrow marks are going or leaving the node x2. You can see here. So we cannot consider these points for the finding the equation. So therefore always remember, the property of signal flow graph is you need to consider only those nodes which are entering towards the node, not leaving the node. Okay, so therefore leaving the nodes do not have any kind of concern towards the entering node. So this is the another property of signal flow graph, which says if the nodes are entering to one particular point, does not have the effects on the branches which are leaving those particular nodes or points. Okay, so this is property number 5. Okay, so what is property number 6? Here is the last property of signal flow graph. Okay, so the last property of signal flow graph says, for a given system, okay, signal flow graph is not unique. Okay, for a given system, the signal flow graph is not unique. Many other graphs can be drawn by writing system equation in different manner. Okay, so that is the big difference between your signal flow graph and block diagram. In block diagram, okay, we need to follow the proper rules and the proper procedure, but here in signal flow graph you can draw the signal flow graph of your own shape. Okay, so that is the difference, and that is the property says that the signal flow graph is not unique. It may change based on writing the system equations. Okay, how the system equations is nothing but it may differ. Okay, the system equations may change. Here you can write here as 4x1 plus 3x4 minus 2x3. Okay, even if you interchange these variables from left to right or at the center, the answer remains same. So therefore in signal flow graph, the system equations are, even if you change, it will not change, and The second thing is all the signal flow graphs are unique. Okay, so with this, all the 6 property, we can simply go for finding the equivalent signal flow graph for any of the block diagram, okay, given. With this, I conclude the today's class.